In Chapter 10, we are again going to continue talking about momentum, and specifically in this chapter, we're going to look at what happens when objects collide. So lots of collisions in this unit. As always, we start off with some new language, some new definitions that we're going to introduce, and the first bit of new language that we're going to introduce is the word impulse. So we are going to look at what the definition of impulse is in physics. And the one thing I need you to keep in mind right from the start is that in impulse, well, it's a new word for us and it's going to be a new definition, is not a new concept at all. Impulse in physics is delta P. So anytime you see the word impulse in a question, you can put a line through it and just write delta P in above it, because that's what it's asking you to calculate. If it's asking you to calculate the impulse, if they give you the impulse, it will be in units of momentum and will refer to the change in momentum of an object during a collision. So you'll see the reason we do this is that it becomes convenient language to use when we're talking about collisions, because collisions happen in a really short amount of time. Now, one of the questions always that we have is, well, how much time is a short amount of time? When is a collision, and when is it just an interaction between the two objects? Well, typically, the collisions that we observe in real life are obvious collisions, like car 1 here hits car 2. So if I have car 1 here hits car 2, that interaction does not last very long. There's a big boom, and we would even use the language collision. There was a car accident, a collision between two cars. You will not have to worry about, do I need to determine whether it's a collision or an interaction? They'll actually use the word collision in the problems where they want you to assume that it's a collision. Now, when we do this, the force between the cars we call the impulse force, right? So again, it's just language that is being used, but it's still the force on car 1 by car 2, and of course, action-reaction pairs still apply. The force on car 2 by car 1 has to be equal in magnitude, opposite in direction. And this is one aspect of what we're doing that I would like you to highlight or underline. I'll underline it here because I do not have it highlighted, is that when we are looking at the force that the cars exert on each other, we are definitely now looking at the force on one car as an external force on the other car, and by looking at the change in momentum of an individual car, we'll calculate the force of the collision. And this is definitely a departure from the center of mass analysis of the two-car system that we've talked about in Chapter 9. And you'll see on our very next page of notes on our second lesson here how that is being applied to problem solving. But when we are looking at the change in momentum, for example, of car 1, right? If I'm focusing on the change in momentum of car 1, that comes about because of the force that car 2 exerts on it. And again, we are departing from our coupled system approach, and you will not have to, again, worry about, well, do I do that? Don't I do that? It will be specified for you clearly in the types of problems we are solving. Now, the last thing that I am going to cover with you on this introductory page is a little cautionary tale of force graphs. So, when we have force graphs plotted previously to what we are doing here, we had this type of situation, right? We had force on the y-axis. We have x on the x-axis. So you have to be very careful about what's being plotted on the x-axis, because the graphs can look identical, right? So you can have the identical functions, right? Identical functions, but they have totally different meaning depending on what's plotted on the axis. So if x is plotted on the x-axis, then we go back to the area underneath the graph is the work done by the force. Work done equals change in kinetic energy. If it's a conservative force, it will also equal negative the change in potential energy. Everything we've done before. However, if time is plotted on the x-axis, now we have the change in momentum. So the area under the force graph, as it's shown here, will equal the change in momentum. So again, please make sure you get this down into your notes, because oftentimes on quiz and test questions, based on energy and momentum maybe being in the same question, you have to be extremely careful as to what is plotted on the individual axes. And now, as I said, in our next lesson, we'll have an example problem to talk about looking at these large collision forces, because, as it says here, the delta t's will be very small, and when their denominator gets really small, it makes for a very big number, a very big force in this case. So that is our introduction with some new language and giving a flavor of what this chapter is going to be on.